So next question, verify A star B equal to 2A minus 3B on the set Z is binary operation or not. So take one counter example here. A star B is defined as 2A minus 3B. A equal to 2, B equal to minus 1. A and B are integers. That means A and B belongs to Z. Substitute 2 star minus 1 equal to 2 into 2 minus 3 into minus 1. 2 2s are 4. Minus into minus is plus. 3 1s are 3. So 7. 7 is also an integer. Therefore, star is the binary operation. Next question. Verify A star B equal to A by 2B is a binary operation on the set or. This one also we prove by taking counter example. A equal to 1, B equal to minus 2. A and B are real numbers. A star B is defined as A by 2B. Substitute 1 by 2 into minus 2, that is 1 by minus 4. 1 by minus 4 is quotient number. Quotient numbers are subsets of real numbers. So minus 1 by 4 is also a real number. If the resultant belongs to given set, then we can say that the given operation is binary operation. Here the resultant is minus 1 by 4 belongs to capital R. Next, the definition of group. Let capital G be a non-empty set. That means G contains elements and star is a binary operation on G. That means if you take any two elements of G and perform the operation, that is A star B is also an element of G, is called a group if it satisfies the following axioms. First one, closure law. Closure law definition is nothing but binary operation definition only. That means for all A comma B belongs to G, A star B belongs to G. Associative law. For associative law, we need three elements. Those three elements are also elements of G only. A star B star C equal to A star B star C. This is associative law. Next, existence of identity element. That means for all A belongs to G, A star E equal to E star A equal to A. Here E is identity element that is also belongs to G only. Next, existence of inverse element. For all A belongs to G, there exists A inverse belongs to G such that A star A inverse equal to A inverse star A equal to E. This is G1, this is G2, this is G3, this law is G4. If G satisfies these four axioms, then we say that G is a group with respect to the binary operation star. Next group is commutative or abelian group. In addition to these four axioms, if the algebraic structure means a non-empty set G together with binary operation is called algebraic structure. if this algebraic structure is already group. Why it is group? It is satisfying all these four axioms. In addition to these four axioms, if G satisfies commutatively with respect to star, then we can say that G comma star is an abelian group. Commutative law means for commutative law we need two elements A and B. A star B equal to B star A. Then we can say that G comma star is an abelian group or commutative group. Next group is semi-group. If G satisfies only closure and associative laws, then it is called semi-group. Semi-group with identity. If G satisfies closure law, identity law and associative law, then it is called semi-group with identity. Semi-group with identity is also called monoid, order of a group. Next definition is order of a group. The number of elements in a group G is called the order of the group and it is denoted by order of G. Here I am giving one example. If G equal to 1 comma omega square, it is a group with respect to multiplication. Then order of G equal to 3 because it contains 3 elements. Next example, G equal to 1 minus 1 I minus I and the binary operation is star. Then order not star multiplication. Order of G equal to 1, 2, 3, 4. G contains 4 elements, therefore order of G equal to 4. Is n comma plus a group? Here one question is there. That question is n comma plus is group or not? N comma plus is group means it must satisfy closure, associative, identity and inverse laws with respect to plus. First of all, we want to show whether closure law is true or not. That means take any two natural numbers, add those two natural numbers, then we are going to get natural number only. That means closure law is satisfied. Associative law. A plus B plus C is equal to A plus B plus C for all A comma B comma C belongs to N. If we take any three natural numbers, then this must be true. Therefore, addition is associative on N. Next, identity law. Here the operation is addition. Additive identity element is 0, but 0 does not belongs to N. Here you can observe identity elements or inverse elements are always belongs to given set only. Here the identity element is 0 that does not belongs to N. So we can easily say that additive identity element does not exist in capital N. Therefore, it is not a group. But here closure law and associative laws are satisfying. Therefore, we can easily say that N comma plus is semi-group but not group. Here, next question is N comma cross is a group? You already know group means it must satisfy closure, associative, identity and inverse laws. Once observe closure law, Consider any two natural numbers, multiply those two, then we are going to get product as AB. That product is also belongs to n. Therefore, we can easily say that multiplication is closed. Next, associative law. Consider three elements of n for all a, b, c belongs to n. A into bc equal to ab into c. This is also true if we take any three natural numbers. Therefore, multiplication is associative on n. Existence of multiplicative identity element. Multiplicative identity element is 1. 1 belongs to capital N. That multiplicative identity is 1. 1 belongs to n. Therefore, identity element is also existing. What is the duty of identity element is any element of n into 1 equal to any element only. So this is true. Therefore, identity law is satisfied. Next, inverse. Here I am taking A belongs to capital N. For this A, the multiplicative inverse is 1 by A. But 1 by A does not belongs to N because 1 by A is a quotient number. Therefore, inverse of A does not exist. Here closure law, associative law, existence of identity element. These three laws are true. Therefore, n cross n multiplication is an example for semi-group with identity. That means it is a monoid. Next one, Z plus is a group. Here also we want to show closure law. Next, associative law, existence of identity element, existence of inverse element. If these four are true, then we can say that Z plus is a group. For this, consider any two integers, add them, then we are going to get an integer. Therefore, closure law is true. Associative law, take any three integers belongs to Z, then A plus B plus C is equal to A plus B plus C is true. This is true for any values of A, B, C. That means any values, any integers. Identity element. Here, addition is the binary operation. Therefore, additive identity element is 0. So, 0 plus A equal to A. Also, A plus 0 equal to A only. This 0 belongs to Z. Therefore, identity element is also existing in Z. Now, inverse law. Additive inverse is if A is an element of Z, additive inverse is minus A. That is also belongs to Z. For example, if 2 belongs to Z, additive inverse is minus 2 belongs to Z. If minus 2 belongs to Z, minus of minus 2, that is 2, belongs to Z. Therefore, for each A belongs to Z, there exists minus A belongs to Z such that A plus minus A equal to identity element 0. Therefore, inverse law is also true. Therefore, closure, associative, identity, inverse. All laws are true. We can easily say that Z comma plus is a group. And also we can verify commutative law. For this, consider any two elements of Z, A and B belongs to Z. A plus B is equal to B plus A. Therefore, addition is commutative. Here Z comma plus is group. In addition to these four laws, it satisfies commutative law. Therefore, we can say that Z comma plus is an abelian group or commutative group. Next is Z comma cross is a group. Here the operation is multiplication. Here also we want to show that group means closure law, associative law, existence of identity element, existence of multiplicative inverse. Closure law. Consider any two elements of Z, multiply those two elements, then the resultant is also an integer. Therefore, multiplication is closed. Associative law. Consider any three elements of Z, A into B into C equal to A into B into C. This is also true for any values of A, B, C. Identity element. We know that multiplicative identity is 1. 1 belongs to Z. That means any integer into 1 equal to again the same integer. Therefore, 1 is the identity element. Inverse. Here, if we take an integer, A belongs to Z, the multiplicative inverse is 1 by A. But 1 by A does not belongs to Z because 1 by A is a quotient number. Therefore, multiplicative inverse does not exist. So, we can easily say that it is monoid. Monoid means a semigroup with identity element. It is not a group.